I'd like to welcome you to this talk on the solar energy output and whether it affects the Earth's climate or not. Just right from the beginning, the talk emphasizes more on solar physics, so the solar variability, and I touch a little bit on the climate issue. However, I don't do climate research myself, but I mean it's very important to have. To nevertheless be aware of the issues. Now, as you all know, the Sun is our closest star, of course. It is 5 billion years old, and a star, of course, is different from planets because it produces its energy in the core. And so in the case of the Sun, we have a core that is of the order of 50 million Kelvin hot, and hydrogen fusion takes place in the core. Now this energy has to be, of course, transported outward. It can't stay in the core of the star, so it passes through the radiative zone in the Sun, and then we have the convective zone. And from the convective zone, the next layer is the photosphere, and the photosphere of the Sun is at a temperature of about 5,800 Kelvin. And the photosphere emits the visible light. And we also see some, due to stellar activity or due to solar activity, the photosphere also shows sunspots, and I will show you more on of sunspot. Now, depending on light at which we look at the Sun, we see, however, still different layers. So that is, oops, it should be up to 10,000 Kelvin. So this is the chromosphere. But I mean, I call it chromosphere, although it's observed here in the images observed in the EIT, but the chromosphere is also it's a layer outward of the photosphere. And now further out we have the corona, which gets to temperatures of a few million degrees. And again, if we observe the Sun in yet another light, we can observe short-term changes, and these are associated to flares. And also on the polar regions and also in the equatorial regions, we can get coronal holes, which are the place actually where the solar wind is accelerated. And just to give you a few numbers, the radius is of the order of 700 megameters, as I remember it, so 700,000 kilometers. And that's of around 100 Earth diameters, so this is the next slide. Oops. So if we look at the Sun, we can kind of put in 109 solar Earth in the diameter. Another measure which I recently thought about is a photon needs to pass the solar radius roughly 2 seconds. So if you ever forget how large the Sun is, maybe you remember the 2 photon, the speed of light. I mean, the photon needs 2 seconds to pass from the center to the. Now, just as a comparison, the Sun-Earth distance is 150 million kilometers, so that's roughly 200 times the solar radius. And the composition, as the Sun is a main sequence star, so it's mainly consists of hydrogen. There's roughly 9% helium. If you count it, these are ratios given by atomic particle density. And the rest are higher elements, so from lithium to zinc. So actually, if we look at the sun in comparison to other stars, the sun is actually a pretty boring star. It is called a main sequence star. And stars that are on this main sequence, they behave in a very characteristic way. And they don't show really a very dangerous or very active, are not in very active conditions. However, in a few billion years, the sun will evolve to a red giant, and you might have heard that the red giant, if it becomes a red giant, its size will be even to the distance where Earth is right now. But of course, this doesn't affect us. And after this stadium, the sun will then become a very hot star, a hot and bright star. So here is actually the magnitude and the spectral class. So it will become a very hot and blue star. And at that time, it will then at some point even throw away its hydrogen outer layers, the hydrogen envelope, and it become a planetary nebula. And finally, the sun will end up as a white dwarf. So this is the end state of the sun. So this is just for you to put the sun in the bigger picture of other stars. Now, well, let's go back to the system, to the solar system. So here's just a scale, because you're well aware the sun is pretty big compared to our planet. Now, the sun is of course, has a certain surface temperature, and it emits radiation. And a lot of the radiation is emitted in the visible light, that is from 400 nanometers to basically 800 nanometers. However, the electromagnetic spectrum covers the range from very short wavelengths of the order of angstrom to X-rays, ultraviolet, and then infrared, and also radio emissions. So, I mean, when we, well, of course, we should never look into the sun, but when we, well, our eyes see, of course, the visible light, but we have to be well aware, and many observations are done in the other wavelength ranges. And the reason, or the motivation to observe the sun in other wavelength ranges is we see different layers, as I already pointed out in an earlier slide. Please interrupt me if something is really unclear or you have questions. Okay, now we, I mean, we observe the light that is emitted by the sun, and many, astronomers, they observe the stars, and that's actually the light emitted by stars and by the sun is a very, very powerful means to analyze the physics that is observed. So therefore, I would like to just briefly point out a few details that come up later in the talk about the emission of light. So we have, the sun consists of a number of, or a whole bunch of atomic species, which are partly ionized. And each of these species has a very, very characteristic energy configuration. So we have really discrete energy levels in each atom, and we can observe these energy levels by looking at the light that is emitted. So consider we have an atom, and two electrons are at the ground state. Now, by collisions of the atoms with electrons, and or by incident radiation, the electrons can be excited to another level, or can even be the atom can even be ionized, which is indicated with the red. So the red is considered to be beyond the binding energy. And now these excited levels, or the free electron, they can now, at a certain time later, can de-excite to the ground level, possibly, or this red electron can recombine with the atom, and emit a certain light with a certain energy. And the level of excitement depends on the temperature in the plasma. So by looking at the light, we can infer details about the temperature, and then also about the structure, because it also depends on the density of the plasma. We can learn about the composition, because we know each of these elements, from hydrogen to, let's say, zinc, they all have characteristic energy levels. So we can learn about the composition of a star, the density, and even the velocity. So the wavelength that is emitted by the plasma also depends whether the gas moves or not. So, and this is the Doppler effect you might be familiar with. So it is very important for you to know that the light we can observe is a very, very powerful means. Now, not only can we learn about temperature and density, we also can learn about the magnetic field. And this goes back to Mr. Zeeman. He discovered that certain energy levels that are so-called degenerate, and please, if you're not familiar with these terms, it doesn't matter. Now, in the presence of magnetic field, a level can split into different other levels depending on the state of depending on the characteristics of the atom. And so in the end you can learn, that the light that is emitted has a certain characteristic. And this characteristic depends on the magnetic field strength. So in fact, so again, with the light that is emitted, we learn about the temperature, density, composition, and we can identify magnetic regions on the sun. And these magnetic regions, they are also very, very important, because most of the variability that the sun undergoes depends on the magnetic field. So when we look at a sunspot, we can this so-called Zeeman splitting allows us to infer how strong the magnetic field is on the surface of the sun. Okay, so I hope you I could convince you that light is a very powerful means to study physics. Now this is a typical spectrum that is observed with a SIM instrument that has been built here at LASP and is operated on the source satellite. And it shows you the wavelength, the solar spectrum from the UV to over the visible wavelength range from 400 to 1,000 nanometers, and over to the infrared wavelength range. Now, what you notice is this is not a smooth function. It is so a smooth function would be the so-called Planck function. A Planck function is emitted by a body that has a certain temperature and has a certain characteristic depending on the temperature. And now the solar spectrum, however, is not a pure Planck function. And the reason is that, first of all, it has structure in it, so the temperature changes in the atmosphere. So we have hotter layers in the interior, and then the temperature decreases and then rises again. And so, for example, an absorption line indicates that the temperature has a decreasing profile. So this is yeah, this is the typical visible infrared spectrum. And now with another instrument, the Solstice instrument on the source satellite, the solar group observes the spectrum in the ultraviolet. And note there is a strong emission line. This is the so-called Lyman alpha line. And I will come back to the variability of the Lyman alpha line in a little bit. Again, we have this function is also kind of close to a Planck function, but it has due to the absorption in the solar atmosphere, it's not a pure Planck function. Okay, now in the solar irradiance group, we want to understand more about the observed light. And well, let me quickly go back. So now, all these features, they are not really observed at the highest resolution possible. They show, I mean, many absorption lines are basically hidden in the observation. So if we want to learn really the detailed physics of the sun, we need to do calculations. And from these calculations, we can then infer, you know, in more detail, we can infer the structure and the density of the solar atmosphere. So just to give you a brief ideas. So these kind of lines, they are emitted by molecules. So whenever we see such features in the solar spectrum, and this is now really at high resolution, which couldn't quite be observed with the instruments I've shown before. But if we have molecules, that means the temperature can't be very high in the solar atmosphere. It has to be at a certain temperature. So whenever we see these features, we know that the temperature is of about 4,000 kelvins or even lower. Now, this is these are calculations done in the extreme ultraviolet. So the blue lines are calculations we have done, and the black lines is observation. And if we are able to match the observations with our calculations, we are pretty sure that we understand at what density is the light formed and at what temperature. Because all these lines, they can only be observed at high temperatures because they are at a very high ionization state. And we can also do detailed calculations of just single lines. But these are just examples. Now, and from these calculations, we then know roughly what the temperature structure of the solar atmosphere looks like. Now, this is only kind of a cartoon, but it should visualize the main points. So we have the photosphere, again, at around 5,800. And then just right at above the photosphere, there is the so-called temperature minimum, which is really at pretty low temperatures. And then higher up is the chromosphere, the transition region, and the transition region actually connects to the corona, which has a few million degrees. And now this fascinating feature of the solar atmosphere that we have a temperature minimum at a certain layer, but then a rising profile. This is not at all, well, I wouldn't say not at all, but it is not really explained why, what are the physical mechanisms that heat up the outer layers to such high temperatures. Okay. Now the thing is, we don't have only a gradient or a change in the height, but we also have features on the solar surface that have also need to be considered when we talk about solar variability. Now, this is an observation. So this is a sunspot observed in the CN. Well, it's an ultraviolet, observed in the ultraviolet light. And what you can see is we have granulation. This pattern, kind of a boiling pattern on the solar surface, is called granulation. And then this nice sunspot is darker because it has a lower surface temperature. And and the center of the sunspot is called an umbra, and the outer layers or the outer regions of the sunspot are called penumbra. Later in the talk, I will show how sunspots influence the total amount of radiation emitted by the sun. And just for you to have an idea about the size, the sunspot can easily get the size of the Earth. So if we could see the Earth passing by, I mean, it might as well be of this size. So sunspots can actually become pretty big. Another feature that also influences the energy output of the sun are the so-called Plage regions. These are bright regions observed in the calcium-2 line in the UV at 393.6 nanometers. And these features, they can occur around the sunspots, but they also can occur in isolated positions, and they are, they enhance the UV emission. So a sunspot decreases generally the energy output. Now the Plage regions, they can enhance the energy output. And note all this, the fine structure here. This is what is called the network, and the network is also influences to a certain extent the energy output. And now, if the thing is, if the sun gets more active, we might see more we see more sunspots. We also see more Plage regions, and in the end, it is the Plage regions that add to the solar to the energy output and increase the total solar irradiance. And just to give you maybe an impression or some insight, the sun is not static. It's changing on large time scales, but also on time scales of seconds. So this is a limb observation of the sun observed with the Hinode, and in fact it's the solar optical telescope on board of Hinode. And what you see is roughly an hour of the movie, and then these the so-called specules, they move really at a very short cadence. And what you might imagine is that these specules all move along magnetic field lines. So the whole variability of, or a lot about the variability of the sun is influenced by the magnetic field. Okay, and here we have some other manifestations of the fact that the magnetic field really influences the brightness of, or the energy output of the sun. So these are coronal loops, and they get to a temperature of, again, of a few million degrees. And further down, the foot points of the coronal loops are associated to the transition region. That is the region where the temperature really rises to high values. So again, the magnetic field is very important for the energy. Okay, and here we have some other manifestation of the magnetic field. This is the corona observed in white light during solar eclipses. And you can see the shape of the corona also follows the magnetic field lines in the corona. And these features are called streamers, and in these streamers the solar wind is actually accelerated. And here we have a nice feature of these so-called diamonds, or at least in German they are called, it's called diamond ring. And this is an observation taken, of course, also during an eclipse. And these structures are due to the fact that the moon has some structure. So you can see a tiny little bit of the solar disk when there's a little structure on the lunar surface. Okay, and finally, one more manifestation of the magnetic field. So this is a huge prominence, and observed in the extreme ultraviolet in the medium light on board the EIT instrument on SOHO. And just to give you an impression, these features can get up to 35 Earth diameters, so they can really have a very huge spatial dimension. Okay, and to give you maybe an impression how the sun looks now in different wavelength ranges, we've just seen the sun in white light, how it changes and how dynamic it is. Now, this is now an EIT image, and now we just saw a flare going off. We can and these features are called coronal mass ejections. So they these are eruptions from the sun, and they carry a lot of the solar mass into space, and potentially also to the Earth. So again, we see under each of these bright features there is an active region. So and all these features show that the magnetic field is again very important. It's the main driver for solar variability. Now, we've seen there are many features that change on a temporal and spatial scale. And now, how about if we just look at the integrated solar spectrum? Remember, I've shown you the curve, the spectrum observed with the SIM instrument. Now and the solstice instrument. Now, if we add up this energy over all wavelength ranges, we get to the parameter that's called the total solar irradiance. And now the total solar irradiance has been observed from space for about 3 solar cycles. That is starting kind of from 1975. And it has been observed by many instruments, and you see a huge scatter of this parameter. So first of all, I mean, it's not due to this scatter between the instruments, but you can see there's a certain variability that is observed by each instrument. So first, the solar constant, which is another term usually used for the total solar irradiance. This parameter is not constant at all. It changes over the so-called solar cycle, or the 11-year solar cycle. So what is plotted down here is the sunspot number. This is a measure of how many sunspots, how many of these dark magnetic features are visible on the solar surface. And as you can see, we have times where there is only a low number of sunspots, or maybe almost no activity. And then we have times when there's higher activity, and this pattern repeats as with a frequency of about 11 years on average. So we see all these observations indicate that there is a certain correlation. Now the problem here is each of the instruments observes kind of a variability of 0.1% or 1,000 ppm. And I show this plot because I want to convince you that it is utterly important to have ongoing space observation, because only if we are able to combine all these measurements to one time series, we will have an ongoing record or a continuous record of the TSI. And so this is now shown in the next plot. So this is a composition of all these different observations I've just shown you, relative to a certain, to one reference observation. And now with these observations, it is clear that also the total solar irradiance behaves like the sunspot number I've shown you in the previous plot. And it correlates very well with this 11-year solar cycle. Or it's a manifestation of the 11-year solar cycle. And the scatter you see in this plot is, it's not an instrumental noise, but it is due to all these solar features on the sun. So whenever there's a big sunspot, the TSI, the total solar irradiance, might decrease to a certain value. And if we have, for example, a lot of Plage regions on the sun, it might go to higher values. I'm not sure whether you can see this big dip here in 2003. So this was a time when there was a really big sunspot passing on the line of sight. And I would like to show you a movie. This is in courtesy of Greg Kopp. He put it together. So this is the source TIM irradiance measurement here as a function of time, of course, from mid-September to mid-November. And whenever a sunspot passes kind of, the field of view, and in particular at the disk center, you see that the TSI changes. So now there's a big sunspot passing by, and the TSI is decreasing, and it's even further decreasing when this huge sunspot, or the two sunspot groups pass the field of view. And actually, these one of the sunspots was responsible for a huge flare that went off during that time, and even caused quite some, caused a huge geomagnetic storm. And I'm sure Frank Eparvier will talk more about these space weather events in 2 lectures. Okay, so this is how solar activity influences the total solar irradiance. Now, the ultraviolet light, which is plotted here, this is the Lyman alpha line. This is the strong line I've shown you in an earlier plot so it's a UV line. So the Lyman alpha variability actually shows even a higher variability. So if you look at the numbers, we get almost an an increase by a factor of 2 over the solar cycle. So these are all the solar cycles. Yeah, the 11-year solar cycles. Sorry. Yeah, so the UV varies much more than the total solar irradiance. And now, what is the reason for this cyclic behavior? Now, to indicate, to just show you what is considered to be the main driver of the solar cycle is magnetic field strength on the surface of the sun. So these blue images are images taken with a Michelson Doppler imager on board SOHO. And in fact, they use this Zeeman effect I pointed out earlier. So this instrument is able to give us information about the magnetic field strength on the solar surface. And the white and black or white and dark blue areas are areas of opposite polarity. So in one case, the magnetic field is pointed outward, and in the other, it's pointed inward of the solar surface. And of course, the magnetic field can we observe it, of course, in any field direction, so any direction is possible. And this image indicates soft X-ray observations taken with the Yoko or the Yoko satellite. This is just to illustrate the solar cycle dependence from over the 11 years, and we have active phases and quiet phases. Okay, and just to show you how this magnetic field looks like or evolves over the solar cycle, look at the movie. And the magnetic field has some pretty interesting features. So what you see is we have here areas of opposite polarity on the northern hemisphere, where the white is the leading polarity and the black is the trailing polarity. And now if you look at the southern hemisphere, it's the reverse polarity. It's just it's the opposite. And this is very characteristic. And this characteristic actually helps us to identify whether a new cycle has started or not, if the sun is quiet. And this is what happens these days. If you look at the magnetogram and you see a polarity that has the opposite polarity from the previous cycle, then this is an indication that the new cycle has started. And in fact, the new solar cycle did start. I mean, there was a lot discussion whether this the present solar minimum is a very extraordinary minimum, or whether it might even become an extended minimum. But as it turns out, the new cycle has already started. Now, another manifestation of the solar cycle behavior are these kind of so-called butterfly diagrams. And what they show is, they show in fact the position where a sunspot has been observed as a function of time. And you can see there is a clear kind of pattern that is very repetitive. That is the new cycle starts. The sunspots of a new cycle always start. They emerge at higher latitudes, and later in the cycle, they are formed closer to the equator. And so this is a very typical pattern for each of the cycles. And as you can see now, this includes the latest observations. We have here a few dots that show already new sunspots of the new cycle that emerge at a high high latitude. So the old cycle is more or less over, although there's always an overlap between the old solar cycle and the new solar cycle. But the new solar cycle is kind of picking up. So, and this is called the Hale law, this pattern. And now another very interesting characteristic, and this also goes back to Mr. Hale, is that the magnetic cycle of the sun actually has a 22-year. It is repeated every 22 years. So, and this is indicated by this plot. Now we have the blue, the green, the yellow color shows positive polarity, and the blue color shows negative polarity. And as you can see, this is the pole region, and every 22 years the polarity of the poles is again has again the polarity of not the previous, but the one before the previous cycle. So the magnetic cycle of the sun is actually a 22-year cycle. Okay, so let me now come.
How do the sunspots line up with that cadence, with that cycle?
Actually, I mean, so what you can see here is also this butterfly pattern. So actually, all these, I mean, the blue and the yellow are magnetic areas on the solar surface. So, and they include sunspots. Does this answer your question? So I mean,
the sunspots are happening at the switch from plus to minus in the magnetic field.
Yeah, I mean, they can. So you can have sunspots that one shows the one polarity and the other another polarity. Although sunspots can also emerge with one polarity only. So I mean, there's no strict rule to that. But
yeah, I was just saying that the peak in the sunspots, it looks like, is occurring at the place where it goes from yellow in the south to yellow in the north.
The peak in the sunspots, you mean the higher latitude? I'm not. Or do you mean the
sunspot cycle seems to be having the peaks of sunspots at the place where the magnetic cycle is switching from plus to minus or minus to plus.
So you mean kind of this area here?
Yes.
Well, yeah. I mean here the sunspots just emerge at a higher latitude.
Mm-hmm.
And later in the cycle they appear at lower latitudes. Yeah, I'm not quite sure whether does it answer your question?
Yes, later.
So now let me talk a little bit more about how we can learn about the spectral variability over the solar cycle. So in the solar group, we try to reproduce the spectral variability and to understand where the spectral variability, I mean, what are the best means to describe the spectral variability. And to do that, we take measurements taken with a precision solar photometric telescope in the calcium line I've shown you earlier, and also in other wavelength ranges. And we do a certain feature identification of the features on the solar surface, and we can come up with these masks that indicate different intensity levels on the solar sun. So we have sunspots, we have sunspot penumbra, umbra, faculae, plage, active network, quiet network, and intergranular cells, just to give you an idea what the features can look like. And now the thing is, each of these features is considered to emit a very characteristic spectrum. And if we do the feature identification each day, then we know how much area is covered by each of these features. And we can weight the spectrum that is calculated from these features, and then derive a temporal variability of the spectrum. And this is shown in the next plot. And this is now the most what I go into detail, but it should show you that we can reproduce, or Jerry Harder and Juan Fontella, who published this work, we can reproduce the spectral variability. Oops. At certain wavelength ranges. So that means we understand to a certain extent the spectral variability. However, in the ultraviolet, it looks a little different. It's not so easy, but I don't want to really go into detail here. For the remainder of the talk, I would like to discuss a little bit the energy output of the sun over the past centuries and even further back in time. So now we have seen the sunspot. I mean, the sun shows this 11-year solar cycle, and the big question is, how did the sun radiate in the past? Because if we want to understand whether it influences the Earth's climate, we need to know, did it change over the past? And there has been work done by a number of people to try to reconstruct the total solar irradiance back in time. So work has been done to do it till the 1930s or even longer. And as you can see, the scatter of this the reconstruction methods they give really different results. So this is a problem. Nevertheless, let's see whether the total solar the energy output of the sun has an influence on climate. And now, first of all, I would like to discuss the present time. That is the time when we have a strong increase, an extraordinary increase in the Earth's temperature, and compare it to the total solar irradiance again observed from space. And this is has been published by Klaus Fröhlich. And the important point here is that, well, we have this 11-year solar cycle, and it seems to be more or less constant. But however, if you do a certain kind of smoothing to the data, then you end up with a red curve. And this red curve indicates that the overall trend of the total solar irradiance has a decreasing trend. Now, if we do the same detrending with the temperature curve I've shown you in the other slide, it clearly shows that the temperature over the past good 25 years has an increasing trend. So this indicates that at least the total solar irradiance cannot explain any change or the recent change of the temperature increase. So I would like to go. I would like you to take home with you that the latest temperature increase is not due to any solar effect, but it is clearly anthropogenic. And this has also been published, or this goes in line with what has been published in the IPCC report, where global circulation models, and they took an ensemble of 14 global circulation models, and they modeled to what extent, and they tried to model the increase of the temperature, of the observed temperature, that is the black line over different areas of over different continents, and the blue shaded curves, these are results from the models using only natural forcing, so no anthropogenic forcing was used. And as you see, all the blue curves, they miss the observation. I mean, they cannot reproduce the observations. And only if we use the anthropogenic forcings, that is the greenhouse gases, only then can the observations be reproduced. And so the final result of the IPCC report is that the confidence level is higher than 95%, that the recent temperature increase is due to is anthropogenic. Okay, now let's go even further back in time. Now this figure shows again the sunspot cycle as observed from 1600 to the present time, basically. And as you can see, and of course the sunspot cycle is an indication of the solar activity. But as you can see, we have areas where we have almost no solar activity, and also some other areas that show kind of a minimum compared to the other to the peak values of the other solar cycles. So, and this long period of 1650 to 700 is called the Maunder minimum, where basically, I mean, there's only a little tiny bit of solar cycling left, but basically the observed sunspot number was very low. And the Dalton minimum that's observed, or that's been manifested between 1800, let's say 10 and 1830, also shows low activity, and there's also another minimum. So now these times with low activity, they are associated, at least in Europe, sorry, this is a little Europe focused, but they are associated to cold temperatures in Europe, where very cold, and these times are, or the time during the Mount minimum is also called the Little Ice Age. But also
Didn't this time when you have fewer sunspots, you should have more solar radiation, right? So why it's colder?
Yeah, that's the very big question. What was the level at which the sun radiated during that time? So I mean, so your point is because of the missing dark features on the sun, the radiation would be higher. Yes, but if for example, if these Plage regions also are not there, then yeah, it might. I mean, the main question is how, to what extent does the quiet sun radiate, or what is really the quiet sun? How much light does, or radiation does it emit? So it is actually unknown. Yeah. How much unknown to yeah, the radiation of the sun during the Mount minimum is unknown. Although people try to reconstruct it, but there are many open questions like did the sun just miss sunspots and didn't have any Plage, or it could as well have Plage regions and then it would be brighter, or what did the network do? You know, these little small scale features on the sun was there any network present? Yeah, so this is kind of open.
Could you say something about what the instrumentation was to measure sunspot numbers in the 1600s?
Well, I mean, Galileo, the telescope, so it was the invention of the telescopes, and
okay.
with the invention of the telescopes, they started continuous observations.
Thank you.
Yeah, and actually it is, the sunspot cycle is also called Schwabe cycle, so this goes back to yeah, the German name. Okay, and actually, so to my knowledge, these people knew each other who observed the sun, and there was they even exchanged letters about this peculiar lack of sunspots. So it's not only that people didn't observe the sun, it was really communicated between people. Okay, yeah, so these are the cold regions, but maybe paintings don't convince you. I'm not sure. Some of you might be scientists, so you are not really convinced by paintings showing any indication of climate changes. Are musicians in the audience? So now, so this has been raised recently that during the Mount Minimum, during this little ice age, the wood that grew through these cold periods has a very is very hard and has special characteristics. And apparently Antonio Stradivari, he lived during, just towards the end of the Mount Minimum, and as you know, he built the Stradivarius, which are now sold, or well, people buy them for a few $1 million, I think. So they have extraordinary sound characteristics, and you might not be convinced by my point I'm making here, but nevertheless there has been even a publication about it. So people studied the wood that was used during that time, and they find really, yeah, the tree ring analysis, for example, is one method. So they concluded that during that time, it must have been very cold, and possibly the slow-growing wood might have helped the Stradivarius to be so yeah, extraordinary. Okay, so now let's go back to real science. So this is now. This is a study that has been put together by Tom Woods and Judith Lean, and it shows, it's a global circulation model, and it shows the differences in temperature using solar input at solar minimum conditions and solar maximum conditions. And what I would like to point out here is that we get the differences between the two model runs are local warming effects. Well, some of them are pretty pronounced in the Antarctic, and then local cooling effects. But the average global warming is 0.1 Kelvin over the solar cycle. So so this might indicate that solar forcing can be a driver to a certain extent to the global warming. And of course, the ideal way to analyze this is not only to do global circulation runs with the solar minimum state and the solar maximum state, but do transient runs. That means to include the full, the time-dependent solar forcing. But nevertheless, these results indicate that the sun has some influence. Has some effect on Okay, so now I would like to finally, oh yeah, should I maybe stop?
I think we can do it. Is this the last slide?
Yeah, it's not quite. I was talking too much.
Maybe show a couple of
let me finish maybe with an outlook of upcoming upcoming missions that where LASP is involved. So and which hopefully help us to understand more about the spectral variability and also its influence on climate. So there is the Solar Dynamics Observatory with the EVE instrument on board, which is kind of waiting for its launch opportunity sometime this year. And then there's the GLORY spacecraft with a TIM instrument, with total irradiance monitor on board. And this is also expected to launch this year. And then there's the upcoming THESIS, the total solar irradiance sensor